Good evening. Welcome, everybody. So my name's Colm. I'm a senior principal engineer. I work at AWS. I focus on our networking and cryptography, like network cryptography, encrypting things. And I'm here to talk about Amazon VPC, Virtual Private Cloud, and get into some of how it works under the hood, and what it does, how you can plug it together, and how it can be used to build secure networks. So I give a version of this talk. Oh, I should probably give it my first slide. Sorry. I give a version of this talk. Some of the content's overlapping. Last year, just digging into how VPC works, and during that talk, just as an aside, unrehearsed, unplanned, totally unapproved, I let something slip that I should not have, maybe. And I got a lot of stick for it. I've heard nothing, but stick for that from my colleagues for the last year or so. I just let something small slip that people can take offense at, and I'm gonna, make an apology and just ask your forgiveness, because I'm probably gonna do it again a lot throughout this talk, and that's about how I say the word root. So it's unavoidable. I was actually lead engineer on our service Route 53 when we built it, and I said root from day one. Most of my colleagues say route. I don't really understand why. We actually, in one of our customer surveys, we send out these annual customer surveys to get feedback on how we're doing. We even put a question in a few of the years saying, well, how do you say it? Because we figured if our customers could tell us, that would at least solve the dilemma. And it came back almost 50-50. Almost exactly 50-50, root versus route. There seems to be no consistency, and some people say both. But I say root, and if you're offended by that, I'm really, really sorry. And like I pointed out last year, I'll say there's just an unambiguous way to solve this problem, which is everybody says Route 66, right? So that must be the right one. And I'm going to use the word a lot. There's no way of avoiding it. So we're going to talk about how VPC actually works, how we send packets between boxes, and what's going on. To understand all that, we're going to cover just what is a VPC. It's this logical abstraction, but we're going to go deeper than that on that. We're going to talk about the role that modern secure web service APIs play, like the difference between that and the legacy network where you just plug things in. We're going to cover how traffic gets from A to B, how it gets into and out of VPCs, and how it gets between things like instances that are inside VPCs, how our packet level security actually works, and how our connection level security works. So that's what we're going to cover. There's a lot to get through. Okay, so what is VPC really? So you're probably already familiar. VPC stands for Virtual Private Cloud, and it's virtual, so it's an abstraction. On our side, it's software defined. And when you create a VPC, what we're letting you do is create your own virtual data center, right? We create some state in our EC2 and VPC services that say, hey, customer wants to create their own virtual data center, and we give them a name for that. It's got an ID that we give back, and that's theirs now. They get this box that is their network or your network that you can launch things into. And you can launch things like instances, right? So regular EC2 instances, very similar to servers. You just run a box, run whatever you want on it. You install Apache and be serving web requests. You can also launch containers inside of a VPC, right? If you want to run Docker images and so on. We have support for a bunch of other higher level services. Things like relational databases, so you can launch an Amazon RDS instance into your VPC, and all sorts of other things. So you can launch an elastic load balancer into your virtual data center. You can launch elastic cache instances, have these caches. You can have private link services, which we'll get to later. All sorts of things. But the idea is, these live in your virtual network. And your instances can reach each other, your containers can reach each other, and your containers can reach your instances, and your instances can reach your containers. And those virtual services that you launch inside, you can reach all those too, everything's reachable. But they're in that secure, abstracted virtual data center. By default, they can't reach anything outside, and nothing from the outside can reach them, right? And then because it's your virtual data center, you also get to pick, the IP addresses it uses. When you create a VPC, you give it a subnet. In this example, we've got 192.168/16. So we're just saying, like, this is the IP range I want to use. You need that control because you're going to connect this later to other existing networks. All those IP ranges need to be unique, right? So that's there, which is pretty cool. Every single VPC that you launch, right, comes with a bunch of things. It's got built-in DHCP service, so that's the service that gives the box its IP address, tells us what its DNS servers are. We have a managed version of that. We also have a network time service, so you can have NTP speaking to your boxes and giving them reliable time. We have DNS infrastructure that comes with it all as well, right? So you can create private DNS entries using Route 53 private DNS, and those will resolve for you in your virtual data center, but they won't work anywhere else. We've got 2 built-in firewall technologies that come with VPC. We've got network ACLs, which are stateless and just let you, block or allow IP ranges and simple definitions. And we've got security groups, which lets you define, collection of instances or containers and allow or block traffic from those. And those are stateful, so they're doing some more advanced kind of rule enforcing on the packets, which we'll see later. And it's a modern network. It can support huge packet sizes up to 9,001 bytes if you want to use jumbo frames, things like that. And all of this is free. You create a VPC, you get all that. There's no charge, right? Which means you can create a lot of VPCs if you like, and some of our customers do. We see customers who create VPCs for their development stacks, their pre-prod stacks, and then sometimes we see customers who create VPCs for like each team to give them their own virtual data centers that they can kind of explore and innovate in without needing to interfere with one another. And we see customers who use VPCs to implement immutable infrastructure patterns, right? So they like stamp out their whole infrastructure in a VPC, and then they never change it. If they want to iterate, they stamp out a whole new VPC with all new infrastructure and all the changes, and then they test it, and then they do this weighted migration to it, and then they turn off the old one, right? Once traffic has drained, which is awesome. And so straight away, I hope you're seeing patterns that just are completely impossible with legacy physical networks, right? This kind of compartmentalization that you can do very easily and by default, right? Just building these abstracted virtual data centers in seconds using APIs, would literally take minimum weeks in the physical world, right? Like ordering physical servers, plugging them in, giving them dedicated L2 connectivity with switches and routers and so on, and then fencing them off from one another. It's very, very hard. So it's opened up whole new architectures. And then the other kind of big difference by default in how these networks operate, how VPC operates compared to legacy networks, is that everything I just talked about, all the provisioning, launching instances, launching containers, connecting things to one another, launching other services inside your VPC, it's all done with like modern secure web service APIs, right? So the only way that I can launch an instance inside a VPC, the only way I can put a network interface inside a VPC, we call them elastic network interfaces, ENIs. The only way is for me to call a secure web service API, right? I compare that to, in my old life as a network engineer, just plug a cable in, right? That was the default way. And that means that we get a lot of security benefits in terms of being able to track who did what when, right? Like who launched that instance, why, when. We've got audit trails in the form of AWS CloudTrail. We've got metrics for everything with CloudWatch. We've got config, which is a service that essentially scrapes your current configuration periodically so that you can easily manage about like time and point-in-time snapshots of like what everything was, and if you want to be able to roll back and so on, it makes it easy. And we've got CloudFormation if you want to build a whole virtual data center using a template, right? All stuff that would just be impossible effectively in a physical network where you're plugging things in. And that's a really big difference. To me, that's actually the biggest security benefit of a VPC, right? Because I've built networks that were like really well locked down in terms of the network data plane, so that I had all the right settings on every switch port, and I had all the right controls in every place so that traffic couldn't be spoofed or man in the middle or anything like that, right? Like a box just couldn't show up and say, send an ARP packet and say, I want that IP address, and just take it over, which is the default behavior, right, on Ethernet networks. Now, that doesn't work on VPC. You can't do that on VPC because we're all about security first. But you can get a network to work like that, right? You can configure all the switches and do that. But it's really, really hard to replicate all of this stuff, all of the, who did what when, and how it's all provisioned. That's much, much harder to do. So I think of that as one of our biggest kind of differentiators. And then, so we can create our virtual data center. We can launch things in it securely, right? And we can reason about what's connected to what, and we can very easily audit it, and we can check the states. But we also need to get traffic in and out, right? That's kind of the next biggest job that we have to do at a VPC. Building a network in a cave that can't actually send or receive traffic would not be very useful. And so we've got a few different connectivity options for getting traffic in and out. You can connect your virtual private cloud to your own on-premises using our Direct Connect offering, right? So you can work with us and our network of Direct Connect partners to get real physical connectivity, fiber in the ground from some premises all the way into one of our Direct Connect locations, and that'll show up as connectivity into your VPC using Direct Connect Gateway. And we have a VPN service, so you can encrypt that. You can use that in combination with Direct Connect, or you can use it just standalone, so you can do a VPN over the public internet, and that's another way to get private connectivity in and out. When you do that, you've got full control over the routing in your VPC, so you can decide, this range goes here, this IP range goes there. Everything you're used to if you're used to managing, real physical networks and you've got access to routers and switches and so on. All of this, we also have full support for IPv6. So if you want to send and receive IPv6 traffic, that works too. And then we've got internet connectivity as well. You can launch an internet gateway or a NAT gateway. And if you want to be able to talk to the internet, you need to be able to reach things that are out there. That works too. The difference between an internet gateway and a NAT gateway is, as you might guess, the NAT gateway does NATing, network address translation, which just means you can hide hundreds of instances or containers behind a small number of IPs, which is useful if you need to whitelist those IPs in remote firewall configurations and things like that. In this example, right, which is really common, where we're connecting a VPC to on-premises, one of the biggest challenges our customers have faced, one of the hardest things to do, has been to get like a really consistent DNS experience between on-prem and VPC. We have our private DNS service that runs inside the VPC, but those private DNS names don't work if you're on premises. And then often customers also have their own DNS servers or Active Directory servers or whatever on premises, and they have their own private namespace for, say, a corporate domain that works on premises on the corporate network, but then those names don't work in the cloud. This has been a big pain point. So last week, we made this a bit easier, hopefully. We actually launched support for Amazon Route 53 Resolver for hybrid clouds. So what this is we'll launch a managed DNS resolver into your VPC, and it can do bidirectional domain forwarding. So you can configure it so that, from the VPC, if you get a query for a certain domain, it'll forward it to your on-premises DNS servers, and they can handle it. And it can also work the other way around, where if you set up forwarding on premises, it'll come into the cloud, and makes this much, much easier, hopefully. I was playing around with this myself last week, and it was pretty cool. So that's the hybrid case, right? But then, whether you're using Direct Connect, or if your traffic is coming in from the internet, either because you're using VPN or because you've got, internet source traffic, like if you're running a public website or something like that. Traffic comes into VPC via the global AWS backbone, right? So that's a backbone we've been building over the last many, many years. Peter DeSantis talked about it last night in his Monday Night Live presentation, and we'll be talking a bit more about it during the week at other presentations. But we've got this huge global network with just huge amounts of capacity that is interconnecting all of our peering locations and everywhere where we accept traffic globally. There's a few kind of important security implications that has for you. So first is this is it's a modern managed network, so everything is locked down in terms of there's no facility for spoofing or man-in-the-middling traffic or anything like that on that network. We secure it at various layers in several different ways. There's some defense in depth there. It is huge amounts of it are under very tight physical control, like for example where the links emerge and actually go into data centers and so on. There's a lot of just real-world physical security around all that, making sure that everything is as it should be, and then we always strive for excellent performance and availability and so on as well. But built into this backbone, right, part of our edge network, so that's those locations that traffic first arrives at when it's coming in. We have quite a lot of DDoS mitigation infrastructure that we've built over many, many years. We have a service called AWS Shield. It's got kind of two flavors. There's Shield Standard, which is every customer gets by default at no charge, and that's you get this always-on inline traffic monitoring and filtering where packets are actually going through and our DDoS mitigation platforms are making sure that traffic is healthy and safe. And we occasionally do see attacks and so on at some of our customers, and these systems just kick in and can start scrubbing the traffic and do all sorts of smart mitigations, including proprietary ones that we've developed in-house using our years of experience that I've never seen elsewhere, that are pretty awesome. One thing I want to say here though is we're a big network. We've got lots of customers, so we have dedicated DDoS response team, and it's something we deal with and have expertise in. But truly, it's a relatively small set of customers who actually ever get real DDoS attacks, right? It's not a huge concern. It's not something you need to be losing sleep over, thankfully. But if you do think you're at a heightened risk of DDoS, right, and there can be things which make you a more likely target than others, and sometimes you become aware through threat intelligence and so on. We also have AWS Shield Advanced, which is much more of a hands-on relationship where we includes direct access to our DDoS response team, and we have calls and we talk to you. Okay, we can do the packet scrubbing and we can do the the first line filtering, but let's look at how your caches are configured. What are your TTLs like? Let's look at how your auto-scaling configurations are. Are you really prepared to scale up if you need to? And we also look at some of the financial aspects of a DDoS, right? Like we make sure that if you do see this massive increase in load, that instead of it being an availability hit, it's just going to turn into a financial hit. So we look at that too, which is pretty cool. And then last night, I had to update my slides today. because last night we launched 2 new offerings in this space related to our AWS Global Backbone. So hopefully you've seen them. But one is AWS Global Accelerator. So what AWS Global Accelerator is you can now use our global backbone for high availability and performance. If you have a service that's hosted in EC2, you can use Global Accelerator to say, well, let's say that service is just in one region, right? Rather than the packets having to traverse, mostly the internet and get onto our backbone somewhere close to that region, and then entering our network and us taking it on from there, we'll do it the other way around. We'll take the traffic as soon as possible, as close to your user, even if that user was at the other side of the world, right? So we will carry the traffic as far as possible. And since we know and are constantly monitoring our AWS Global Backbone Network very, very well, we can route around any issues. We can manage latency and congestion and all those kind of things. And then you get all those security benefits too, where it's traversing a network where traffic can't be spoofed, right? Where traffic can't be intercepted. Most internet transit networks these days do try to prevent spoofing. But there's still a sizable percentage that don't, right? And especially in certain parts of the world, there can be a good chance that your users' packets might traverse a network where traffic can actually be spoofed or intercepted, which usually isn't what you want. You don't want to give third parties the ability to disrupt traffic like that. It's got all sorts of other non-security features too. It can be used effectively as a sort of global load balancer. You can use it to send traffic to multiple regions, and it supports proximity-based routing and weighted routing and failover configurations with health checks and all that kind of stuff. And we also launched last night AWS Transit Gateway. So what AWS Transit Gateway is essentially lets you build your own flexible border network, right? So you can launch, instead of having, if you've got multiple VPCs, instead of just connecting them to the internet independently or creating your own kind of peering mesh and your own transit VPC that traffic comes into and then you do stuff with it and it goes out, it's a really common pattern. Transit Gateway can do all that for you. And it includes a bunch of features that are targeted for security. It supports routing domains. So you can have configurations where you say, look, all north or southbound traffic has to go over here before it then goes in or out. And so you can build DMZs with this, right? You can build a layer where, say, a central security or network team owns it and manages it and enforces certain controls. And if you want to route all traffic through, say, an IPS, you can now do that, which is pretty awesome. And it's going to become more and more featureful over the next year. I'm really excited about some of the stuff that's coming. So that's how traffic gets in and out, right? That's kind of that's kind of traditional network routing in a sense. Like we're doing all sorts of due diligence. We're doing all sorts of, we're paying attention to the security configuration, making sure everything can't be spoofed and so on. But really, it's traditional layer 3 networking, right? That's what's happening, especially out there on the internet, right, where we have no control. But inside of VPC, things are quite different, right? Inside of VPC, so as we saw earlier, you can create your own VPC and you get to give it your own IP range. Now, 2 customers or 3 or a million can do that, and they might have the same IP range, right? So we can't just put those packets on the wire, right? It wouldn't work. They wouldn't go to the right places. So clearly something else is going on, right? And that's what I'm going to get into. So when you launch an instance, right, those are virtual servers, right? They run in a virtualized environment, and there is some physical server somewhere that has those, right? There's some physical server that's actually running the virtualization and launching those instances. And if you're running on a bare metal host, you essentially get the whole blue box here, you get the whole physical host. But in either case, right, attached to that physical host, like physically attached, part of the box, right, we have our own embedded router that we have built. And it uses Amazon designed, Amazon built, Amazon operated hardware. So 4 years ago, we acquired a company, a chip manufacturer called Annapurna Labs, who, they start with chip designs and they go all the way to fabricating it and everything in between. And we work very closely with them to build this actual embedded router that sits inside the physical host and does all of the virtual networking, right? And because it's in hardware, we can have a lot of hardware enforced security. And because it's this dedicated kind of miniature appliance that's right there, it's not taking any resources from the server that's running your instances. And that's part of how we can do bare metal, for example. That's how we can give you the whole box, right? Because effectively we have this other little box that's actually doing the things we need, which is kind of cool, right? And these boxes are amazing. Working on them, something I've gotten to do over the last few years, it's like living in the future, because like you're working on chip designs that are a few years out because they have to be taped out and then they go to manufacturing plants and so on. And it's amazing to see like how the insane levels of performance that these things can achieve. Like last night we launched a new instance type that can do 100 gigabits per second, right? And still do like all of the stuff that I'm about to talk about, all of the packet manipulation, all the security features that I'm about to talk to. Like it's kind of staggering. And so what this embedded router is doing is it is doing the translation from the virtual network, right, from your VPC to something that can go on the wire and be routable, right? And so we actually encapsulate all the traffic. We have our own software-defined networking protocol we call Novice that we've been using for a long, long time. We've iterated on it a few times, made some adjustments that keep improving performance. But it's not an off-the-shelf protocol that you've seen out there. But it is an encapsulation layer, right? So the packet that you send, the packet that your instance crafts, when it wants to send traffic, from instance A to instance B, gets wrapped in our encapsulation and then put on the wire on the physical network, right? And that's how all the traffic is disambiguated. For traffic between instances, for traffic between containers, all that stuff that's in the VPC, this is all just how it works. Packets come in, packets go out, and they all look like this. If packets need to leave our network, they obviously need to be translated back into like regular looking packets. We need to take that encapsulation off. And that's the job of a platform we call Blackfoot. We have these Blackfoot edge devices. And those essentially are responsible for taking encapsulated traffic and stripping our layer off and then sending it on to the internet or direct connect or VPN or something like that for external traffic. And they do it in the other direction as well. If packets come in kind of plain, they'll add the encapsulation and pass it on, which is pretty cool. And then, so in that encapsulation, right, the outermost IP address, like the one that's actually on the wire that the network sees, essentially says, like, this is the physical host that I need to get this packet to, right? And then there's some other stuff in there, some metadata that says, and here's the instance and the network interface on that instance that I need to get to, right? And that's what's going on. It's actually quite simple. But like, how does the sender know these, right? When a physical host on one of those embedded routers gets your packet, how does it know what these values should be, right? So we have an internal microservice, part of our network control plane, that we call the mapping service, right? And so we have this mapping service that's running, and it has, like it sounds, this big map that maps, this virtual network interface, this virtual private cloud corresponds to this physical IP address over here. This is the actual server that's hosting it. This is where you need to send that traffic so that at the other end it can understand. It's a broadly distributed web service. It's internally one of our bigger web services. It is really, really fast. There's some caching going on to make things super, super fast, because the lookups, like the lookup time that we have when we get a packet from you to determine like where it can be sent and then add that encapsulation is tiny. We're in the nanoseconds to microseconds range to achieve the levels of throughput that it takes. It's not a lot of time to consult something. So, rather than have it being like this remote fetch where it has to find the mapping, it's much more of a like proactive push kind of situation where we're constantly pushing these mappings out and things are ready to go. It's pretty cool. And this, mapping service, because we have this level of abstraction and enforcement, this is what provides a lot of our data plane security too, right? This is why traffic can't be spoofed or just intercepted on a VPC, right? If an instance just sends traffic for an IP address that doesn't belong to it, or tries to send an ARP packet to like hijack an IP address, it doesn't work because this whole layer is intermediating that, right? It's actually looking at the network interface and saying, well, I don't care what your packet looks like, I'm just gonna stamp it with this network interface and this physical IP address no matter what, right? And then the same happens at the other end. So when the packet is received, we actually look up the mapping service as well and see, well, does the mapping service agree that like that packet should have come from there? Like, is that a valid destination for that traffic too? Which is very similar to a system called RPF, reverse path forwarding, that you see in like internet networks. And it means that we can make this core kind of guarantee about VPC, right? That your traffic is under very tight control. You're not going to see boxes hijacking each other or anything like that, which is great. That helps me build a lot of things. And so that's kind of like packet level security, right? That's what we're doing in terms of, hey, I just want to be able to put a packet on the wire and make sure that it gets to the right place. But we also do flow and connection level security, which is even much more advanced, where we're actually looking at the flow. So say a TCP connection from like a client, like a web client going to say port 443 because it's a HTTPS request. We're doing a bunch of things to make sure that traffic is also secure, right? That traffic isn't going haywire or that nobody can play with it. Some examples of that, right? So security groups include stateful connection tracking, right? So that means, when you open a connection, you send this SYN packet, and it's got a certain sequence number, and it's got certain source ports, and so on. And we just make sure that all subsequent packets match that, right? That incoming packets can't just be spoofed out there on the internet, whatever. And if it happens to, match like just certain aspects of that, like the destination port will let it through. We actually put pretty tight limits on that. We also do flow logging, right? So you can actually see. We'll give you a log of every flow that we've observed, right? Which is a really, really advanced feature on other networks, enabling NetFlow, for example. But we can do that because we're tracking all the flows. We can say, look, here's the flows we've seen. You can feed that into like an IDS or similar systems if you want to do threat intelligence based on that, if you want to, or even like service dependencies based on that, see what's calling what, which is kind of cool. We have a product called Network Load Balancer, right? That can do large-scale flow balancing for you. And that's actually built into the fabric of VPC. It's not like this virtual appliance or something like that. It's like built into the VPC network where it can, take traffic and balance it across targets at ridiculous scale. It can do millions of connections per second and millions concurrently, and we think probably terabits of traffic. We don't even really know where the ceiling is, which is kind of cool. And then we have NAT Gateway, which is doing like per flow, stateful NATing for outbound traffic, right? You want to connect to something out there on the internet, but use NAT. Well, we do proper, full, stateful, enforced security on all of that. So, like, how are we doing all this, right? Well, a lot of this is actually enforced on those embedded routers again. They're actually doing connection tracking right there as close as possible to your instances so that the security can be right there. And if you look at what goes into a flow, what they're doing is pretty simple. If you've ever run netstat on a machine, you'll see a large table of active flows, and every flow is identified by a 4-tuple, right? You've got a source IP, a destination IP, a source port, and a destination port. Actually, the protocol's included too, so it's really a 5-tuple. And for our purposes, since we include VPC, it's actually really a 6-tuple. And we're just tracking that, right? We're just making sure that every single packet matches all of that. And not just those aspects, but we also look at the sequence and ACK numbers, right? So when a connection is established, it's got a random sequence number that's important so that connections can't just be spoofed. And the responder has a random ACK number for the same reason. And we track that those numbers also line up and match across everything. This is for TCP. For UDP, things are a little different. For UDP, there's no sequence and ACK numbers, but UDP traffic can be fragmented, and fragments are supposed to have the same ID, and we do track all that. It's pretty cool. Am I one slide behind? I don't think so. It's pretty awesome. And so I mentioned a bit about NAT gateway and network load balancer already. And these are built on top of a platform that we call Hyperplane. So we've got this, everything we've seen so far is relatively implementable just in those embedded routers. They can just track and enforce everything that they need to right there and then. But when you start using NAT gateway or network load balancer, or actually AWS Transit Gateway, which we launched last night, we start to need distributed state, right? We start to need to track things in a distributed way on more than one machine because we're making promises that we have to keep for long periods of time. Like for example, if network load balancer or NAT takes a connection and decides it should go to a certain place, we need to make sure that all subsequent packets for that flow go to the same place, right? And to do that, we actually store or record our decision on multiple machines with a lot of redundancy so that we can survive any kind of failures and so on. And so how does that work, right? And how do we do that securely? So the way that works is underlying all these services, we've got this system called Hyperplane. And Hyperplane nodes are built, they kind of slot into the network in a similar way to Blackfoot that we saw earlier. If you create a NAT gateway or now a transit gateway or an NLB, what's really happening is we're provisioning some Hyperplane nodes for you under the hood and setting up mappings in our mapping service that says, look, traffic that's destined for those locations should go to the appropriate Hyperplane nodes, right? And then traffic comes into Hyperplane, it does its thing, right? It can share state in tens of microseconds. So if it gets a new connection in and says, hey, pick a target to send that to, it makes that decision very quickly, records it very safely, and then starts forwarding the flows very robustly. In the NAT case, it allocates source ports at that phase. We have to assign a unique source port to every outbound connection, so that's what's happening there, right? And this whole system is actually just for best security practices, right? This is a big, sensitive system that's connected directly to VPC at our, at a very sensitive layer. It has the ability to, intercept traffic and manipulate traffic. And so we enforce some security best practices. We have some, compartmentalization and isolation between these layers. So Hyperplane doesn't actually know about VPC mappings. They're all abstracted for it a little by the mapping service and by those embedded routers. It just kind of knows about flows. And it doesn't really know whose are whose and what's going on too much there. And that's important because in order to be cost effective and achieve tremendous scale, it's a multi-tenant system, right? It's actually handling an enormous number of flows for large sets of customers all at the same time. And this introduces another security problem, right? Which is how do we handle like denial of service attacks or, not even an attack, like somebody just has a really busy day. Like, they've got a Super Bowl commercial and the Super Bowl commercial goes live at, that particular instant and they get suddenly a huge peak. We wouldn't want it to be so that, their nodes get super hot and everybody else suffers, right? That's no good. So we have this pattern, which my colleague Peter Voschel talked a lot about yesterday in a talk. If you want to learn more, look up his talk on YouTube, that we call shuffle sharding, which we use here as a security technique. And it's really simple. The way it works is that, like, imagine we've got a bunch of nodes for Hyperplane. Here I've got 8 on my slide, because that's all I could easily fit. But in reality, it's much, much more, up to like 100 or so. And we give each customer just a random allocation, right? So when you create your Hyperplane resource, I might give you like these 3 nodes. I'll just assign those to you. Other customers run those nodes too, but that particular pattern is unique to you, right? I've only given you those 3, that combination of 3. And so another customer comes along, and I'll give them a different combination of 3, right? So here I have an orange customer, and there might be some overlap, right? Like, so we've got one node in common, the bottom one. And so now if you just think through, well, what happens if, say, the green customer has a DDoS or a peak event? Well, those 3 green nodes are going to get a lot of traffic, right? But that only impacts one of the nodes that the orange customer is using, right? So we actually have some built-in resilience. And the system has built-in redundancy. If it can work around that, slight degradation, things are fine. And that's how we've built it. And the effectiveness for this is like pretty staggering. It's amazing how well it scales up. If we do the math with just the numbers we have here, so we have a service with 8 nodes, and we allocate each customer to like 3, well then, the numbers work out like this. We're saying, okay, 18% of the time, right? So let's say the green customer has a DDoS. 18% of our customers won't notice at all, won't have any impact, won't even be on the same nodes, right? They've got overlap 0. 54%, so the majority, have overlap of 1 node, which is what we saw on the slide. 26% are a little unlucky, they have 2. And then if we were just doing a really naive allocation, we'd actually have 2% of customers who have 3. But that's still amazing, right? Having just 3% customers with full overlap, just using this allocation strategy is kind of staggering. If we do this with some real numbers, so the numbers we actually use for Hyperplane are, okay, let's do 100 nodes, and let's give each customer 5. The numbers are staggering. Like 77% of customers have no overlap, none. 21% have 1 host out of 5 that might have some overlap. And then 2% have like 2 nodes of overlap and so on. And the numbers get smaller and smaller really quickly. They're so small, we can just exclude them because we just, if we ever happen to allocate a pattern like that, we just delete it. We actually check. So we create a pattern. We say, well, what's the overlap for that with any other customer? And if it's too many, we just discard it. And the numbers are so great, we can still allocate millions if we need to of these shuffle sharded patterns. And so that means even in the worst case, right, you've got an overlap of 2 using these numbers, and the system's got more than enough redundancy to handle that. So like without us having to do anything, without us having to step in, without us having to do any kind of like online, inline DDoS mitigation, it just kind of takes care of itself, right? Customer gets an attack or a peak event, their nodes light up, the other customers don't even notice. It's great. And then we actually also take that customer pretty quickly and isolate them and start scaling them up so that their experience is really positive too. We don't want to just black hole their traffic or something like that. That wouldn't be any good. And the same techniques are being used in AWS Transit Gateway. They're kind of at the core of how we manage these multi-tenant security offerings. All of this is actually based on the load balancer that we built for Amazon S3, which is why you see the tremendous amount of scale. And we've been using it since we launched Elastic File System quite a few years ago. So it's got quite a bit of operational experience at this time, and it's been one of our most reliable systems, which is comforting because it's right there in the core of things. And then so since we have Hyperplane, right? Since we have this system that's built directly into our network fabric, can do all these things with flows. Last year we actually launched a new offering called Private Link, which is particularly interesting for securing networks, right? And so what private link is kind of for the first time we made it possible that you could create a load balancer in one VPC, but expose it as a VIP, as an IP address or a network interface in other VPCs, right? And that might seem kind of boring and subtle, but it's actually really profound. And we've seen customers build, very different security architectures back in that. Because what it lets you do is it lets you run your services in isolated, compartmentalized networks that are just for them, and then expose a very small surface area into the other VPCs that can just receive connections, can't connect in, right? So kind of removes a whole set of threats that show up when you have a flat network or a peered network where everything can just connect to each other. And you get these really strong controls, right? You get like fully auditable APIs on both sides that, both sides consent to this relationship and they can both revoke it at any time. And you get all the benefits of flow logs and all that kind of stuff. And it's really awesome. We've been moving a lot of our own internal architectures to this model because we really love that it lets each team essentially have their own network and unblocks them and they can just do whatever they need to do in that network. But we can step back from it and at a mile high say, well, they're still only exposing this one IP address and this one port in the other VPCs. So that's what we have to focus on, pen testing and making sure that it's safe and secure. It reduces everything, which is pretty cool. It has, it's integrated with AWS Marketplace as well. So we have some vendors as well that are now vending services that you can launch inside your VPC as private link offerings. Many of those are security services. We have a bunch for doing like log ingestion as a classic example, which is pretty cool. The main takeaways I want you to take from all this, or hopefully you'll take from all this, is that VPCs are, as the name sounds, they're virtual. They're just abstractions. We're giving you the ability to have your own virtual data centers, which you can, really do a lot with when it comes to securing things, right? Like it's a really big change in mindset to realize I can just have 10 or 100 networks where before I had one, and I can give everything its own little playpen, and I can give everything its own kind of ring fence. That's a very different way of building networks and enforcing security boundaries, and it opens a lot. Our APIs are all auditable and secured. They're all signed, which I didn't mention. So every API call is cryptographically signed and also comes in only over HTTPS and all the kind of modern stuff that you'd expect. It's all there. We have lots of DDoS mitigations. We've given talks over the years. If you want to, again, look at reInvent presentations, just put the string DDoS in there and you'll find lots more rich detail about how we do that. We actually use shuffle sharding there too and how we do some of our DDoS mitigations at the edge. It's pretty amazing. And we can integrate all of this into existing networks pretty easily. We have flow logs and we have firewalls. If you want to use them, you can do all the connection tracking for you. That's usually better than doing it on your own instance, because you've got that secure separation, right? If you just run IP tables on your own host, it works, but like what if the host gets compromised, right? What if they get root on that box? You just turn it off. Well, they can't turn any of this off, right? This is a whole different layer removed. So it's very much like having a separate firewall, which is pretty cool. And then we have these new offerings, including Transit Gateway, which launched last night, which isn't on this list, that let you compartmentalize and separate things, right, and build these ring-fence VPCs. Pretty awesome. If you want to learn more while you're here, I'd recommend all these talks. ACT309 is super, super popular, but like is probably one of my favorites. I'm getting into all this. We've got a talk just on private link, and I've had a lot of customers ask me this week already about private link, so I hope that one will be pretty well attended. And we've got a 400 level talk too on design patterns for VPCs, where we'll get into serious detail. Thanks for coming. We do have time for questions. If you do have any, there are 2 microphones, I believe, and I will do my best to answer. Let's see. Thank you very much.